All right, so I want to talk about another formula that you might see on your formula sheet. It's kind of right underneath this formula here, the lambda is equal to d sine theta over n. There's another formula kind of right beside that one. I'm just going to scroll over here. And it says lambda, it's used in the same situations, is equal to x d over nl. So all these xd's and nl's, we talked about them, like the distance from the antinode to the central antinode to whatever node or antinode you're looking at. That's x. The d is the distance between the slits. The L is from the slits to whatever measuring device you're using, such as a screen or something. And N is just whatever antinode or node number you're looking at. So all this stuff we talked about already, right? But we never use this formula to do any math. So this formula, never used for math. Now the reason we never, I'm just going to say never. Like some people might say, oh, use this if the angle is 1 degree or less, right? I say if it's much less than 1 degree, like it has to be like 0.0, like in the first question down you can see is 0.08 degrees. Okay, yeah, I'm okay. You probably could use this formula if you wanted to do that because the angle's that small. But the problem is, whatever the problem, if you have the angle, just use the other formula. There's no point to using this formula. If you can find the angle to verify that you want to use this formula, then use the other one. And the reason you can't use this for small angles, or sorry, for large angles, because it makes an approximation. It makes an assumption about how long these two lines are, this line and this line. All right? Right now, you can see in this picture, this line over here, that's the hypotenuse. It's larger than this side over here, which is the adjacent, to consider this the angle down here. Right, so those are totally different sizes. The hypotenuse is always longer than the adjacent. But there's something called the small angle approximation. When the angle gets smaller and smaller and smaller, you kind of moving in that hypotenuse. So this angle gets smaller. Okay, now I look at these two again. So they're totally different right over here because they're so big out to the side there. This hypotenuse is huge. But because the angle got smaller, these two lengths, like the hypotenuse now and the adjacent, well, they're getting closer in size. Now, if my angle gets even smaller, they even get closer in size. There's very little difference between these two. And if I get even smaller after that, if that angle gets even smaller, I can almost say that that hypotenuse and that L are the same thing. If the hypotenuse and the L are the same thing, I can almost say that tan theta is equal to, because tan is going to be x over L, and sine theta, which is x over the hypotenuse, if I can say that L and hypotenuse are the same thing, I can say that tan theta is equal to sine theta. Only for really small angles, like really small angles. Like it has to be so small that those two sides can be same. They can be considered to be the same length. Then I can say that these two things are equal to each other. Then I can make the two formulas. So that's that sine theta is equal to, and tan theta, which we know is x over L, because that's just based on just tan trigonometry there. I can replace the x over L, and I can put it into this formula here, where sine theta is. Put x over L in there, and that becomes this formula. There's an x over L there. So there's the d over n in the original formula, and the x over L from the new formula. Now, we never use it for math because it makes that assumption. It makes the assumption that L and the hypotenuse are the exact same size. But they never are. The hypotenuse is always larger than the adjacent. So Sure, it's a really fun thing to say. It's a really good small angle approximation, but I can never really say that they are the same because they never are. So we're making a pretty big assumption there. And this is being compounded by another assumption. We've already assumed that these two lines coming from S1 and S2 are so close together that we consider these two lines to be parallel to each other, which is an assumption already. We made an assumption, then we make another assumption on top of that, which is compounds assumptions, which makes this formula a bad formula to use. Now, the reason that we have the formula at all on the formula sheet is for just to know what happens if I change things. And most of the time, this formula here, I almost want you to just kind of cross this formula off and say x is equal to. Let's rearrange it for x. This is what the formula that we usually use. Just to talk about what happens if I change things. Like, okay, I do the same experiment, say Thomas Young's experiment, but I change the wavelength. I say, okay, now I'm going to use a red light rather than a white light or a yellow light or something. If I change the wavelength, what happens to my x's? If everything else has to stay the same, the distance between the slits, the L's, the N's are all the same, what happens to my x? The distance between all the little bright spots? Well, they go up. Lambda goes up, x goes up. Okay. What happens if my distance between the slits? What if I decide I want to make those slits a little bit closer to each other? What if I say that this goes down? Oh, geez, that's weird. What if I said that goes down? Well, x will also go up. So the slits get closer together, but the pattern that you see there starts spreading out more at the very top because they're inversely proportional to each other. Other ones are more obvious. What if I just move the screen further away? So the L goes up. Well, obviously the X is going to go up as well. So it's all these, just the relationships. So we're only using this for the relationship between the variables. We never use it for the math. Always use the d sine theta one. Okay. So I have a few questions here. Well, I have a lot of questions here until we get this Poisson's bright spot. So I want you to try the next 4 questions. Pause the video if you haven't done so already. Try the next 4 questions. And we'll come back and see if we get the right answers. Okay, so hopefully you tried these ones here. Monochromatic light. So we always do this in monochromatic light because I'll show you a demonstration in a bit here. Well, actually, I can just show you right now. If my lambda goes up, my x goes up so that the interference pattern spreads out. But what if I have all my light, white light coming through? White light is all my wavelengths. It's all wavelengths kind of bunched together to get this white light. That all the different wavelengths are going to interfere at different times. Red light wavelengths will have bigger x values. Violet wavelengths will have smaller x values. So they're going to spread out and create a rainbow. And I'll show you what this looks like. Hopefully I can find I have diffraction gradients. Hopefully this will work through a camera setting. I can show what the rainbow looks like. Right? You do a little dual slit experiment, you can see the rainbow spread out. And the x's are going to be further out than the red light's going to be further out than the violet because the red has a longer wavelength. So it interferes and diffracts at a further distance. All right, so let's go through. Monochromatic light just means one type of light. So it doesn't matter what kind of light it is. We're just going to do the calculations based on that. We have 2 slits, pretty small. They're in millimeters. And if we leave this in millimeters, we're going to get a wavelength in millimeters. I'm just going to change this to meters because I like that. We have an angle, a really small angle. But since we have the angle, might as well just use the formula with the sign in it. Oops. So the formula we're going to use is going to be, is going to be this one here. What do we have here? Oh, the first bright spot, or first maximum, is going to be 1. So our n is equal to 1. So that's, they just tell that to us. But I'm just going to put in my formula here. 0.3 times 10 to the negative 3 times sine 0.08 degrees divided by 1. So that should get me my wavelength here. Yep. So I get 4.19 times 10 to the negative 7 meters. And if I change that into nanometers, because that's negative 7, I could see that this is going to be 419 nanometers. I'm just dividing by 10 to the negative 9, because that's how many meters are in a nanometer. So it does a little flipperoonie there, and you get 419 nanometers. Then you can match this up to some kind of color of light. So that's probably in the greenish range, probably. Yeah, maybe in the bluish greenish range. You can see here's blue. Blue is the same similar number. Okay. What's the angle of diffraction for this one here? So we got a third antinode. Antinode, which is important, is that this is n is equal to 3. Okay, because the third antinode. The two slits here. So we got the d, the distance. So that's times 10 to the negative 3. I'm going to change it from the milli to regular meters. We got wavelength here. It's a nanometer, so I'm going to change that to regular meters so they match. They have to match for the formula to work. And we're trying to find theta. So I'm going to go write my formula here. D sine theta over n. We're trying to find theta, so I'm going to rearrange this for sine theta. So n lambda over d is equal to sine theta. N being 3. Lambda 460. And d is being 0.55 times 10 to the negative 3. You can see my units are going to cancel out there. Sine ratio is always unitless, but that's beside the point. We're just trying to get the angle anyway. I think I got everything. My phone calculator here looks pretty good. Then we're going to take the sine inverse to find the angle. And you can see that the angle is 0.1. I think my calculator's in the right mode. Yeah, 0.14 degrees. So a pretty small angle there. Yeah, looks pretty good. Yep. Like the other one, the angle previously was smaller than this one, so that's okay. Second nodal line. Oh, nodal line. Okay, so they're using a node, not an antinode. So remember, nodes are the dark spots, antinodes are the bright spots. So this is the second nodal line. So if I think about that, so this is n is equal to 0, 1, 2. So these are the bright spots here. My second one's going to be between 1 and 2. So this is like 1.5. So this is n is equal to 1.5. Okay. Produces an interference pattern, occurs. Well, I'm going to have to do, sorry, I meant to put a little thing on here. Degrees, I'm assuming that's going to be degrees relative to the central antinode, which makes sense. The two slits are separate because the angle is always going to be measured towards the central antinode. We won't do it towards between other ones. It gets too complex for that. The two slits are experimented or separated by a certain distance. What's the wavelength and what color do you think this is? So we could just go through this and say this is d sine theta over n. So my d here. If you want to put down your givens, you can. Not too concerned about that at this point. Let's put this angle in there. And I'm going to divide by my n of 1.5 because I'm talking about a nodal point there. Okay, so let's punch out my calculator. So I get a wavelength of 4 point, there's only 2 signigs to everything here, 4.4 times 10 to the negative 7 meters. If I want to put that into nanometers, I'm going to add an extra signig there. So 442. If I compare that to bluish light there, yeah, it's probably a blue violet light. Now green would be on the other side, right? So it's going in this direction. It would be getting longer. So Roy G. Biv. So it's getting shorter than the blue light that we set up there. So it's going to be like in the blue-violet range. Okay. Monochromatic light is instances in 2 slits, and they give us the slits here. So I'm just going to list off my variables again. I didn't do it in the last one, but I'm going to do it in this one. Interference patterns observed on a screen. Oh, that's 5 meters away. Okay, so I'm changing everything in meters anyway. The distance between the third dark fringe and the central antinode. So they've given us the X value at this time. The dark one, so the dark one. So if I go back to that picture we had before, the third one, 1, 2, 3. The third dark spot would be right here, which would be 2.5. Okay, yeah, that's 2.5. So third dark fringe is 2.5. X is 4.50. Now, so if I want to, like I have XDNL, so I know all this stuff. So if I ever wanted to use this formula, which would be XD over NL, I can only use this if my angle is really, really, really small. Much, much smaller than 1 or something, right? So let's determine what the angle is first. So to determine what the angle is first, I'm going to have to use a little bit of trigonometry here. I'm going to draw what my picture is here. So here's my 2 little slits down here on the little piece of paper. So here's my D. And I'm going to label this off. So this is what we have, XLD. And we have the N, so we know what N value this happens to be. This is just the dark spot here. Okay, so there's a little dark spot. So I need to find this angle. To find the angle, tan, I'm going to use tan because I got the opposite and the adjacent, so I'm going to use that to find out what my angle is. So my theta is tan inverse of X over L. Okay, so let's find out what that angle is. So tan inverse oh, 0.515648 degrees. Yeah, it's less than 1. Oh, but now I have the angle. So why even bother using this formula? If I have the angle, let's just use this formula. Why not? So I'm not going to go back here and do this. I got my angle. I'm going to just use that down here. So if you can find the angle, then why ever use the other formula? Which you shouldn't. You should never use the other formula. It's just there for that relationship idea. And divide it by 2.5 here. And I'm going to get the sine of my answer. So I just have my calculator here. Sine of the answer which we just found times my distance between the slits in meters. Divide by the 2.5. Ooh, that's a nice number. 5.4. No, just 5.4 times 10 to the negative 7. I was just looking at sig digs. That's why I paused there for a second. I'm going to just change this to 3 sig digs in nanometers just to see what kind of light it looks like. So it's probably in the greenish range at this point. There you go, or maybe even yellow. I don't know exactly. So again, don't use that formula. If you can find the angle, just use the other formula. So we can find the angle because we're given the X and the L. So we just use the d sine theta over n formula. Okay. There are some reasons, like if I tried the X, let's just double check. You might get the same answer. So if I use the XD over NL formula here for this one, I'm just going to punch it in because I got all the XDs and NLs here. 5, I divide by the 5. You get 5.4 times 10 to the negative 7. Exactly that number. It's backwards, I know, but it says 5.4 times 10 to the negative 7. No decimals, right? The previous one had 5.399 something, right? Because of sig digs and rounding, you end up getting the same number. But if I went to like the nearest hundredth or the nearest thousandth, I might have a different number. So you just have to be very careful, right? So just be very, very careful. Like all these ones here, you probably would have got the same number if you use the XD over NL. Just be careful. Okay, let's double check this one here. Students use the light of a wavelength. So they give us the wavelength, about 500 nanometers. I'm just going to leave it in meters. Distance between the third node, which we already know is 2.5, and the central antinode, so they give us the X value. Kind of weird that they put that in scientific notation. And they give us the L. Yeah, they give us the L value. We want to find out what the D is in this situation. So I could use XD over NL. I could rearrange this for D and get lambda NL over X and do the math, which I am going to do. I'm going to do that right now. I'm just going to plug these in, and then I'm just going to verify to see whether or not this was a good choice to do. All right. Divided by X. So you get 1.5 times 10 to the negative 5 meters. Okay, so they're pretty close to each other. So that's assuming the angle is pretty small. I made the assumption without even looking for the angle. So the idea of this is you want to find the angle. So always find that angle first. So I'm going to use the other formula. I'm not going to use this formula yet, sorry. I'm going to use the tan theta formula, sorry. Shouldn't use that erase button that often because it messes up. So I'm going to use the tan theta formula. I'm going to find the angle because I have an X and L. They're in the question, so I'm just going to use the X and the L to find this angle. Ooh, the angle's 4 degrees. That's not much less than 1. So, I don't know how good that assumption is going to be. Let's double check here. So we're going to compare it against that number up there. So I just found the angle. Because I just found the angle, I can use the other formula. Lambda is equal to d sine theta over n. I can rearrange this for d. I should rearrange it for d instead. So n lambda over sine theta. Okay, we have the n. We have the 2.5. We have the lambda. 5 times 10 to the negative 7. I can divide it by the sine of the answer which we just got. Oh, 2 sig digs. I had an extra 0 on that. 1 times 10 to the negative 5 meters. Different number. The bottom number is more correct because we only made one assumption here. This number up here is wrong, right? Now, you've seen on previous quizzes where you round, if I asked for 3 sig digs and you rounded it wrong, it'd give you the mark instead. On this kind of question, if you round it wrong, you'll get it wrong. Because I'm making an assumption that you used the wrong formula to solve the question. If you can find the angle, always use the other formula. All right. We're going to break this up into a different video, but before I go on, another guy named Poisson did the same thing. We passed a parallel light towards a little disc, and then he noticed that as the light bent around on all sides, not just two sides like a 2-slit experiment, no, it's on all sides, it also produced that same kind of pattern. I don't know if you can, if I zoom in here, you can kind of see they got this bright spot right in the middle where the disk would be. So the disk would be right here where the dark starts. And then you got this interference pattern all the way down, bright spot, antinode, node, antinode, and then you get all the way down to the central antinode right in the middle there. So Poisson did the same experiment, but he just did it with a disk instead. Okay, in the next lesson, we're going to be talking about diffraction gratings. There's only one thing about diffraction gratings. They use the exact same formula as the 2-slit experiments, but they tell us some other different types of information. We'll talk about that in the next video. I'll see you then. Bye.